252 million years ago, something ended, not gradually, not in stages spread across tens of millions of years, but with a geological abruptness that leaves a visible mark in rock formations on every continent. The boundary is thin, often just a few centimeters of sediment, and yet it separates two fundamentally different worlds. Below it, the record of the Permian, dense fossil assemblages, diverse marine invertebrates, complex terrestrial ecosystems, forests, reefs, and a biosphere that had been building in complexity for nearly 300 million years. Above it, almost nothing. The Permian-Triassic boundary represents the single largest loss of biodiversity in the history of complex animal life. Current estimates, derived from multiple independent studies of fossil records across marine and terrestrial formations, suggest that somewhere between 90 and 96% of all marine species and roughly 70% of terrestrial vertebrate species cease to exist within what appears, at geological resolution, to be an extraordinarily brief interval of time. The mechanisms behind this extinction were not singular. Evidence drawn from sedimentary geochemistry, isotopic analysis, and the stratigraphic distribution of volcanic deposits points toward a convergence of environmental stresses operating simultaneously and reinforcing one another. At the center of this convergence were the Siberian Traps, a volcanic province that released, over an estimated 1 to 2 million years, somewhere between 1 and 4 million cubic kilometers of basaltic lava across what is now northern Russia and Siberia. But the lava itself was not the primary driver of extinction. It was what the eruptions injected into the atmosphere that mattered. Carbon dioxide, methane released from destabilized permafrost and seafloor clathrates, sulfur dioxide, and halogen compounds entered the atmospheric system in volumes sufficient to destabilize global climate, acidify rainfall, and fundamentally alter ocean chemistry. Global mean temperatures are estimated to have risen by somewhere between 8 and 12 degrees Celsius above pre-extinction baselines. In shallow tropical marine environments, sea surface temperatures may have exceeded 40 degrees Celsius, a threshold beyond which most complex marine organisms cannot survive. On land, temperatures across equatorial Pangaea reached levels that current physiological models suggest were incompatible with sustained vertebrate activity during daylight hours. Before we continue, take a moment to consider where you're watching from, which country, and how distant it is from the world we're about to enter, where life struggled through the first 10 million years after Earth's greatest extinction. If these journeys into deep time are something you enjoy, consider subscribing to continue exploring them. It's always remarkable to see how far these stories travel. Dim the lights, settle into the quiet, and let the modern world fade as empty landscapes slowly awaken, silent oceans begin to recover, and the first fragile signs of life emerge on a planet still bearing the scars of catastrophe. The oceans responded to these conditions with a cascade of geochemical changes. Elevated atmospheric carbon dioxide dissolved into seawater and lowered oceanic pH, dissolving the calcium carbonate structures upon which reef ecosystems depended. At the same time, elevated surface temperatures reduced the solubility of oxygen in seawater and strengthened thermal stratification, cutting off the deep circulation that normally ventilated the ocean interior. Vast portions of the deep and intermediate ocean became anoxic, depleted of oxygen, and in many regions, euthynic conditions developed, meaning that hydrogen sulfide, a compound toxic to most complex life, accumulated in the water column. Evidence for these conditions comes from biomarkers preserved in ancient sediments, including compounds produced specifically by the anaerobic photosynthetic bacteria that thrive in sulfide-rich, oxygen-free water. The signature of these bacteria appears in Permian-Triassic boundary sections on multiple continents, indicating that the toxic, stratified ocean was not a local phenomenon, but a global one. Reef systems that had taken tens of millions of years to construct were dismantled within timescales that appear, in the sedimentary record, to be geologically instantaneous. On land, the transition was no less severe. The great coal forests that had defined the late Paleozoic, dense stands of tree ferns, lycopsids, corditalian conifers, and seed plants, underwent what geologists have termed the end Permian coal gap. For several million years following the extinction boundary, coal deposits are essentially absent from the geological record globally. Coal forms from the accumulation and compression of dense plant material in stable, wet ecosystems over extended periods of time. Its absence from the early Triassic record indicates that those stable, productive forested ecosystems had largely ceased to exist. What replaced them was not a reduced version of the prior system, but something qualitatively different. Landscapes dominated by opportunistic, low-diversity pioneer vegetation, spore-producing plants, early conifers, and hardy fern communities, capable of surviving in disturbed, unstable, nutrient-poor soils. The terrestrial plant community of the early Triassic appears, from fossil pollen and spore assemblages, to have been both species-poor and structurally simplified. A canopy with dramatically reduced height, complexity, and biomass compared to what had come before. Into this landscape, emptied of its ecological infrastructure, the survivors emerged, and they were few. The vertebrate fauna of the earliest Triassic is remarkable, not for its diversity, but for its monotony. At most fossil sites from this interval, spanning localities in South Africa, Antarctica, Russia, China, and Australia, the assemblages are dominated overwhelmingly by a single genus. That genus was Lystrosaurus. Lystrosaurus was a dicynodont therapsid, a member of the synapsid lineage that includes the distant evolutionary ancestors of mammals. It was a relatively compact animal, with adults of most species ranging from roughly half a meter to just over a meter in body length, though some populations show variation across this range. Its body plan was robust and low to the ground, with a barrel-shaped torso, short limbs positioned in a semi-erect posture, and a distinctive skull featuring a downward curving beak suited for cropping and processing vegetation. Two small tusks, present in some individuals and likely associated with sex or age class, projected from the upper jaw. The animal was herbivorous and almost certainly a highly efficient generalist feeder, capable of processing a wide range of plant material, an attribute that would have carried significant survival value in a world where vegetation was sparse, patchy, and unpredictable. Lystrosaurus had existed before the extinction. It was part of the Permian terrestrial fauna and was not a dominant or particularly widespread component of those ecosystems. But something about its biology, its physiology, its dietary flexibility, its reproductive rate, or some combination of these and other factors, positioned it to persist through conditions that eliminated the vast majority of its ecological contemporaries. What followed the extinction was not simply its survival, but its expansion into a landscape from which almost all competition had been removed. The ecological release that Lystrosaurus experienced was profound. With predator populations decimated, prey communities absent or vanished, and the complex webs of competitive interaction that normally structure vertebrate communities dismantled, the available terrestrial niche space was, to a degree almost without parallel in the fossil record, open. The evidence for Lystrosaurus dominance is quantitative and consistent across geographic regions. At multiple early Triassic fossil localities in the Karoo Basin of South Africa, one of the best sampled continental records for this interval, Lystrosaurus specimens account for roughly 90 to 95% of all individual vertebrate fossils recovered. This degree of numerical dominance by a single genus is exceptional by any standard. In modern ecosystems, even the most successful species rarely approach this level of dominance within a vertebrate community. The Karoo data is not an isolated anomaly. Similar patterns of Lystrosaurus dominance appear in early Triassic deposits from Russia, China, and Antarctica, confirming that this was a genuine global signal and not a local taphonomic artifact. Lystrosaurus had, in functional terms, inherited the terrestrial vertebrate world. The world it inhabited was not hospitable. The landscapes of the earliest Triassic, roughly the first 1 to 2 million years after the boundary, are interpreted from the sedimentological record as predominantly arid to semi-arid across much of Pangaea's interior. Fluvial systems show evidence of flashy, ephemeral flow regimes rather than the sustained river systems associated with well-vegetated catchments. Soil profiles from this interval lack the deep, complex horizons associated with stable, long-term vegetation cover. Wind-blown sediment, preserved as aeolian dune structures and loess-like deposits in some regions, suggests that in the absence of plant cover to anchor the ground surface, dust mobility increased substantially. The atmospheric dust loading of the early Triassic may itself have had secondary consequences for regional climate, affecting radiative balance and precipitation patterns in ways that compounded the already severe greenhouse conditions. Lystrosaurus moved through this world in what appear, from trackway evidence and bone bed assemblages, to have been groups. Bone beds, concentrated accumulations of multiple individuals of the same species preserved together, are interpreted as evidence of gregarious behavior, and Lystrosaurus bone beds from southern African and other localities suggest that these animals aggregated, at least seasonally or in response to resource availability. Gregarious behavior in a resource-poor landscape carries both costs and benefits. Competition for food is intensified within a group, but group movement can facilitate the location of dispersed food patches, and in an environment with active, if sparse, predation pressure, group living offers detection and dilution advantages. The specific ecological drivers of Lystrosaurus aggregation cannot be reconstructed with certainty from the fossil evidence alone, but the pattern of grouped preservation is recurrent and geographically widespread, suggesting it was a genuine behavioral characteristic rather than a depositional accident. The few other vertebrates that shared this landscape with Lystrosaurus occupied narrowly circumscribed ecological roles. Small therocephalians, another therapsid group, persisted in very low numbers. Procolophonid reptiles, small and lizard-like in body form, survived and would gradually diversify over the course of the early Triassic, though they remained minor components of the fauna. Early archosauromorphs, the evolutionary lineage that would eventually give rise to crocodilians, pterosaurs, and dinosaurs, were present, but extremely rare in the earliest post-extinction assemblages. Temnospondyle amphibians, large and semi-aquatic, appear at some localities as the dominant non-Lystrosaurus vertebrates, occupying the margins of rivers and lakes where aquatic food resources, though also diminished, remained more available than terrestrial ones. This is the full scope of the early Triassic terrestrial vertebrate world as currently understood. A handful of lineages, most represented by small populations in restricted habitats, against a background of near-total ecological vacancy. The concept of ecological vacancy is important for understanding what the early Triassic represents in the history of life. Ecosystems are not simply collections of species, they are networks of interactions, dependencies, and feedbacks structured by millions of years of co-evolution. When species are removed from an ecosystem, the interactions they participated in are disrupted, and the resources they consumed, or the habitats they maintained, become available. When 90% or more of species are removed simultaneously, the result is not merely a disrupted ecosystem, but the near-total collapse of ecological structure itself. Food webs were shortened to their simplest possible configurations. Nutrient cycling, which in complex ecosystems involves the activity of countless species of decomposers, herbivores, predators, and their microbial partners, was reduced to its most basic functional pathways. The early Triassic world was not simply an impoverished version of the Permian world. It was a different kind of biological system, operating under different rules and with different constraints. Lystrosaurus existed at the center of this simplified system, not because it was particularly well adapted to the specific post-extinction conditions in any finely tuned way, but because it was generalist enough, robust enough, and numerically dominant enough to fill the role that ecological circumstance had created for it. Its success was not the result of competitive superiority over sophisticated rivals. It had no rivals of comparable body size and trophic position remaining. It was the inheritor of a world that the extinction had cleared. How long this phase of extreme dominance lasted is a matter of ongoing study, but evidence suggests that Lystrosaurus's period of near-complete numerical supremacy was relatively short in geological terms, perhaps 1 to 2 million years. As conditions slowly began to moderate and other lineages gradually recovered or diversified, the proportion of Lystrosaurus individuals in fossil assemblages declined, and the earliest signs of returning ecological complexity began to appear. But in those first millions of years, the record is unambiguous. On a planet where almost everything had been erased, one animal had endured, and for a time, it was effectively alone. Lystrosaurus did not simply survive the end Permian extinction, it expanded across a supercontinent. Within the first million years of the early Triassic, fossil evidence places it in what are now South Africa, Antarctica, India, China, Russia, and several additional Gondwanan and Laurasian landmasses. This geographic distribution is among the broadest documented for any single terrestrial vertebrate genus in the Paleozoic or early Mesozoic fossil record. Understanding how an animal of modest size and unremarkable locomotor capability achieved this range requires understanding the world it moved through, a world in which the usual barriers to dispersal had been substantially reduced, and in which Pangaea's continuous landmass offered, at least in principle, uninterrupted overland access from one region to another. Pangaea, at the onset of the Triassic, was a single coherent supercontinent stretching from pole to pole, flanked by the vast global ocean known as Panthalassa to the west and the shallower Tethys Sea to the east. The interior of this landmass was subject to extreme continentality, the tendency of large land areas far from oceanic moisture sources to experience pronounced climatic extremes, with hot, dry summers and cold winters, and relatively low and unpredictable precipitation. The mountain ranges, inland seas, and forested corridors that, in a more ecologically intact world, would have structured dispersal routes and restricted movement between regions, were, in the aftermath of the extinction, diminished in their effectiveness as barriers. Vegetation cover was sparse and discontinuous. River systems were simplified. The ecological filters that typically prevent generalist animals from dispersing freely across varied habitat types were weakened by the very impoverishment of the landscape itself. Lystrosaurus moved through this landscape with a physiology that appears to have been suited, if not precisely optimized, to variable and unpredictable conditions. Therapsids as a group occupied a metabolic and physiological position somewhere between the ectothermy characteristic of most reptiles and the full endothermy of mammals. Bone histology studies, the microscopic analysis of bone tissue growth patterns, indicate that Lystrosaurus grew relatively rapidly by the standards of non-mammalian synapsids, with growth rings in some specimens suggesting seasonal variation in growth rate consistent with life in an environment where resource availability fluctuated. Rapid growth and the capacity to modulate metabolic activity in response to environmental conditions would both have been advantageous in a world characterized by resource scarcity and climatic unpredictability. Its dietary generalism was equally significant. Lystrosaurus was capable of processing a broad range of plant material, from soft aquatic or semi-aquatic vegetation to tougher terrestrial plant matter. The geometry of its skull and the mechanics of its jaw suggest a powerful bite delivered by a keratinous beak, capable of cropping stems, roots, and tubers at or below ground level. Root and tuber feeding would have been particularly valuable in a landscape where above-ground vegetation was sparse and subject to rapid desiccation during dry periods, because subsurface plant storage organs are more resistant to surface heat and drought than exposed shoots and leaves. The ability to exploit food resources that other animals could not easily access, or that were distributed below the visible surface of the ground, may have provided Lystrosaurus with a nutritional buffer that more specialized feeders lacked. Reproduction also likely played a role in the persistence and spread of the genus. Dicenodonts are not known to have given birth to live young. The available evidence suggests egg-laying reproduction, as in most non-mammalian synapsids of the Permian and Triassic. Egg-laying animals with relatively short developmental times and high reproductive output can replenish population losses more rapidly than species with extended gestation periods, prolonged parental investment, or low reproductive rates. In an environment where populations were chronically exposed to mortality from resource limitation, environmental stress, and predation, the capacity to recover numerically from population crashes would have been a significant advantage. The specific reproductive parameters of Lystrosaurus, clutch sizes, developmental rates, time to sexual maturity, cannot be directly measured from the fossil record, but the pattern of its numerical dominance across broad geographic areas and across a sustained interval of time is consistent with a species capable of rapid population growth under favorable conditions. What the fossil record does reveal directly is the sheer scale of Lystrosaurus abundance in some localities. In the Karoo Basin, which represents one of the most continuous and well-sampled continental records of Permian-Triassic transition environments anywhere in the world, the shift in faunal composition across the extinction boundary is stark. Below the boundary, assemblages contain dozens of genera representing multiple trophic levels: large herbivores, medium-bodied omnivores, small insectivores, and a range of carnivores from dog-sized forms to animals approaching 2 meters in body length. Above the boundary, that diversity compresses dramatically. The range of body sizes present in the earliest Triassic assemblages is narrow. The range of dietary specializations represented is narrow. And Lystrosaurus accounts for the overwhelming majority of identifiable specimens across essentially every sampled horizon. Bone bed sites are particularly informative. At several localities in South Africa and in correlative deposits elsewhere, accumulations of multiple Lystrosaurus individuals preserved in proximity suggest episodes of mass mortality, likely associated with drought conditions or the desiccation of water sources. Animals aggregating around diminishing water supplies in an arid landscape would be expected to die in clustered groups when those water sources failed entirely. A pattern that produces exactly the kind of multi-individual bone bed that appears repeatedly in the early Triassic record. These sites indicate not only that Lystrosaurus was gregarious, but that it was living in an environment that periodically imposed severe mortality events on even the most successful surviving vertebrate lineage. The predators that shared the landscape with Lystrosaurus in these earliest Triassic years were few and generally small. The large Gorgonopsian predators of the Permian, animals that had reached body sizes comparable to large modern carnivores and had occupied the apex predator roles in pre-extinction ecosystems, had not survived. What remained were smaller therocephalians and cynodonts, both therapsid groups, neither of which approached the body sizes that would have been required to routinely prey on adult Lystrosaurus. This absence of large-bodied predators is itself ecologically significant. In modern ecosystems, top predators exert what ecologists term top-down regulation. They limit the population sizes of large herbivores, prevent competitive exclusion among prey species, and maintain the structural complexity of the ecosystem. Without effective top-down regulation, a single dominant herbivore species can expand to densities that would not be sustainable in a fully structured ecological community. The combination of factors that elevated Lystrosaurus to dominance, dietary generalism, physiological flexibility, high reproductive potential, reduced competition, and the near-total absence of large predators, did not produce a stable or particularly productive ecosystem. What it produced was a simplified one. The Lystrosaurus-dominated world of the earliest Triassic was ecologically functional in the most minimal sense. Energy moved from plants to herbivores to small predators through truncated, low-diversity food chains. But the redundancy, complexity, and resilience of a mature ecosystem were absent. The system was vulnerable to further disruption, and the environmental conditions of the early Triassic ensured that further disruption continued to arrive. Despite its numerical dominance, Lystrosaurus existed on a planet that remained fundamentally hostile. Mean annual temperatures across equatorial and mid-latitude regions of Pangaea were substantially elevated relative to both modern values and Permian baselines. Seasonal temperature extremes in the continental interior were severe, with some climate model reconstructions suggesting that summer temperatures in mid-Pangaea may have approached or exceeded physiological tolerance thresholds for sustained activity. The same greenhouse forcing that had driven the extinction had not dissipated. Atmospheric carbon dioxide concentrations remained elevated throughout the early Triassic, and the thermal anomaly associated with the Siberian Traps volcanism persisted long after the eruptions themselves had begun to wane. Lystrosaurus was not living in a recovering world. It was living in the hottest and most chemically disrupted phase of a crisis that had not yet reached its conclusion. The geographic spread of Lystrosaurus across Pangaea should be understood in this context, not as an active, directed colonization driven by ecological opportunity in the conventional sense, but as the diffusion of a generalist survivor through a landscape that had lost its structure. Where vegetation patches existed, Lystrosaurus was present. Where water persisted, Lystrosaurus aggregated. Where conditions deteriorated beyond tolerance, local populations collapsed, leaving the bone bed record of mass mortality that geologists continue to excavate today. The pattern across the supercontinent was one of abundance, punctuated by episodes of severe localized loss, a demographic profile consistent with a species operating near the edge of its physiological limits across much of its range. No other terrestrial vertebrate of the early Triassic achieved anything comparable to this combination of abundance, geographic extent, and ecological centrality. For a period of roughly 1 to 2 million years following the extinction, Lystrosaurus was, by any measurable criterion, the most successful large-bodied vertebrate on Earth. Its success was built not on sophistication, but on resilience, on the capacity to persist where nothing more specialized could, and to reproduce quickly enough to maintain viable populations in a world that continued, in subtle and not so subtle ways, to press against the boundaries of what complex animal life could endure. The early Triassic was not simply warm. It was, by the best available paleoclimate reconstructions, one of the hottest intervals experienced by complex animal life in the entire Phanerozoic, the 540 million year span of Earth history, during which multicellular life has left a substantial fossil record. The mechanisms driving this heat were not mysterious. The Siberian Traps eruptions had injected enormous quantities of carbon dioxide and methane into the atmosphere over a geologically brief period, and the climatic consequences of that injection persisted long after the eruption rate itself began to decline. Greenhouse gases, once added to the atmosphere, are not rapidly removed. Carbon dioxide is absorbed by silicate weathering reactions and by the ocean over timescales of hundreds of thousands to millions of years. In the interim, the atmosphere retained the thermal energy that elevated carbon dioxide concentrations trapped, and global mean temperatures remained high across the full duration of the early Triassic, an interval spanning approximately 5 million years. Quantitative estimates of early Triassic temperature come from multiple independent proxies. Oxygen isotope ratios preserved in marine carbonate fossils reflect the temperature of the seawater in which those carbonates formed, and their values from early Triassic sections consistently indicate elevated sea surface temperatures relative to both the preceding Permian and the later Triassic. In tropical marine environments, these proxies suggest sea surface temperatures ranging from approximately 35 to 40 degrees Celsius during peak warming intervals, values that are at or beyond the upper thermal tolerance limits of most modern tropical marine organisms. Terrestrial temperature reconstructions, derived from paleosol geochemistry and the isotopic composition of organic matter preserved in continental sediments, are more uncertain but broadly consistent with marine records, pointing to mean annual temperatures across equatorial Pangaea that were substantially higher than anything experienced in those latitudes today. The spatial structure of this heat was not uniform. Pangaea's geometry amplified warming in its interior. The supercontinent's vast landmass, stretching from approximately 85 degrees south to nearly 80 degrees north, created an interior that was thousands of kilometers from any oceanic moisture source. Continental interiors heat and cool more rapidly and to greater extremes than coastal regions, because land has a lower heat capacity than water and lacks the moderating influence of oceanic circulation. In a world already experiencing globally elevated temperatures from greenhouse forcing, the interior of Pangaea would have experienced summer temperatures that substantially exceeded the global mean. Climate model simulations of early Triassic conditions, constrained by the available proxy data, suggest that lethal summer heat, defined as sustained temperatures above approximately 40 to 45 degrees Celsius, may have extended across broad swaths of equatorial and subtropical Pangaea during peak warming intervals. The biological consequences of this thermal regime were direct and severe. At the cellular level, proteins denature and enzymatic function breaks down at sustained high temperatures, a threshold that varies among species but that imposes hard limits on the geographic ranges available to ectothermic animals. For reptiles and amphibians, whose body temperatures track environmental temperatures closely, sustained exposure to air temperatures above approximately 40 degrees Celsius is typically lethal. The fossil record of the early Triassic reflects this constraint. Across equatorial Pangaea, vertebrate fossil assemblages from peak warming intervals are notably sparse, not only low in diversity, which is expected, but low in the sheer number of recoverable specimens. This pattern, sometimes termed the equatorial vertebrate gap, is interpreted as evidence that sustained lethal heat periodically excluded vertebrate life from a broad equatorial belt during the hottest phases of the early Triassic. Even Lystrosaurus, the most numerically dominant terrestrial vertebrate of the interval, shows a distributional pattern consistent with thermal stress. Its highest density occurrences in the fossil record are concentrated in mid to high latitude localities: the Karoo Basin of southern Africa, the Transantarctic Basin, and equivalent deposits at comparable paleolatitudes in the northern hemisphere, rather than in equatorial regions. This latitudinal concentration is consistent with animals seeking refuge from peak heat at higher latitudes, where temperatures were elevated relative to modern norms but remained below lethal thresholds for sustained periods. The supercontinent's pole-to-pole extent, which under normal circumstances would have created a diversity of climatic zones, now functioned primarily as a thermal gradient along which life was pushed toward the cooler margins. Aridity compounded the effects of heat. Elevated temperatures increase evaporation rates from soil and vegetation surfaces, drying landscapes even when precipitation amounts remain unchanged. In the interior of Pangaea, where precipitation was already limited by distance from oceanic moisture sources and by the disruption of atmospheric circulation patterns associated with the extinction itself, the combination of high temperatures and low moisture availability produced conditions of extreme aridity across vast areas. Sedimentological evidence from early Triassic continental deposits includes abundant aeolian, wind-blown, sandstones, evaporite mineral deposits formed by the concentration and precipitation of salts from evaporating water bodies, and paleosol profiles showing deep desiccation cracks and low organic content. These are the signatures of desert and semi-desert environments, and they appear across multiple continental sections from different paleolatitudinal settings, indicating that arid conditions were geographically extensive rather than locally restricted. Deserts impose their own distinct ecological logic. Resources in desert systems are concentrated in space and time, around permanent water sources, in seasonal flood corridors, in topographic depressions where soil moisture accumulates. Animals in desert environments must either maintain access to these concentrated resource patches or evolve physiological and behavioral strategies for tolerating resource scarcity between patches. The early Triassic fauna had limited time to evolve such specializations. The extinction had only recently occurred, and the surviving lineages were generalists rather than desert specialists. What the fossil record suggests is that vertebrate populations in the most arid interior regions of Pangaea were sparse, episodic, and highly dependent on the persistence of specific water sources and vegetation patches that were themselves unstable. The monsoon system of Pangaea, driven by the temperature differential between the supercontinent's interior and the surrounding Panthalassa Ocean, delivered seasonal precipitation to portions of the landmass, particularly along its eastern margins facing the Tethys Sea. Evidence for monsoon-influenced fluvial activity appears in the sedimentary record as alternating cycles of channel-fill deposits and floodplain mudstones, reflecting the pulsed nature of seasonal rainfall. During monsoon seasons, rivers rose and floodplains were inundated. During dry seasons, those same rivers shrank to isolated pools or ceased flowing entirely. Vegetation along river corridors was more persistent than in the open interior, and it was along these corridors that the most continuous record of early Triassic terrestrial life is preserved. Thermal stress also affected recovery at the ecosystem level. Plant productivity, the rate at which vegetation fixes atmospheric carbon into organic matter and makes it available to herbivores, is sensitive to temperature, water availability, and atmospheric chemistry. In the early Triassic, all three of these parameters were operating at values unfavorable to high productivity. Elevated temperatures increase plant water demand and, beyond certain thresholds, directly impair photosynthetic efficiency. Water scarcity reduced the area of land capable of supporting sustained vegetation, and the elevated carbon dioxide concentrations in the atmosphere, while in principle stimulating to plant photosynthesis at moderate levels, were accompanied by heat and aridity that offset any potential fertilization effect in much of the landscape. The result was a terrestrial primary productivity that remained substantially below Permian levels for millions of years, constraining the energy available to all higher trophic levels and keeping the overall biomass of the ecosystem depressed. It was within these conditions, sustained greenhouse warming, episodic lethal heat, widespread aridity, and suppressed primary productivity, that the survivors of the extinction attempted to persist and diversify. The thermal maximum of the early Triassic did not arrive instantaneously at the extinction boundary and then immediately begin declining. Proxy records indicate that temperatures remained elevated, with possible additional warming pulses for several million years into the Triassic. The world that Lystrosaurus and its ecological contemporaries inhabited was not a world in the early stages of recovery. It was, in many respects, a world still in crisis, a planet whose climate system had been destabilized and had not yet found a new equilibrium, and whose biological communities were attempting to rebuild in an environment that continued to impose severe and, in some intervals, lethal constraints on their capacity to do so. Predation does not cease when an ecosystem collapses, it contracts. The food webs that support large, active carnivores, complex networks of prey species, prey of prey, and the vegetation that ultimately underlies all of it, were devastated by the end Permian extinction, but the impulse toward carnivory persisted in the lineages that survived. The early Triassic terrestrial landscape supported predators, but they were few in number, restricted in body size, and operating under energetic constraints that no predator in a well-structured ecosystem would have faced. Understanding these animals requires understanding not just their biology, but the conditions that shaped every decision their physiology was capable of making. The search for food in a world where food was genuinely scarce. The great predators of the Permian were gone. The Gorgonopsians, large-bodied therapsid carnivores that had occupied apex predator roles across the late Permian terrestrial world, did not survive the extinction. Some Gorgonopsian genera had reached body lengths of 2 to 3 meters, with skulls bearing elongated canine teeth suited for delivering powerful bites to large prey. They had been the dominant terrestrial carnivores of their time, and their disappearance left a gap in the ecological structure of the post-extinction world that would not be filled by a comparable animal for millions of years. What replaced them, initially, were smaller and more generalized carnivores, from lineages that had survived not because they were powerful, but because they were adaptable. The primary surviving terrestrial predators of the earliest Triassic belonged to two therapsid groups, the therocephalians and the cynodonts. Both were members of the synapsid lineage, and both had coexisted with Gorgonopsians during the Permian in subordinate predator roles, occupying ecological niches defined by smaller prey, lower energy requirements, and greater dietary flexibility. The extinction removed their larger competitors without removing them, and they entered the early Triassic as the dominant carnivorous vertebrates of the terrestrial landscape by default rather than by competitive superiority. Therocephalians of the early Triassic were generally small. Most known forms ranged from roughly 20 centimeters to just under 1 meter in body length, and their dentition suggests a range of dietary strategies from insectivory to small vertebrate predation. Some therocephalian genera show anatomical features consistent with at least partial omnivory, including reduced and differentiated tooth rows that allowed processing of plant material alongside animal prey. In a landscape where prey animals were sparse and unpredictably distributed, dietary flexibility of this kind was not a secondary trait, but a functional necessity. A predator capable of subsisting on insects, small reptiles, plant material, and carrion during intervals when vertebrate prey was unavailable would have had a substantial survival advantage over a specialist that required specific prey to meet its energetic needs. Cynodonts occupied a similar ecological position, though their lineage would ultimately prove more consequential in evolutionary terms. Early Triassic cynodonts were small, likely active animals with differentiated teeth, incisors, canines, and post-canine teeth with more complex crown morphologies than those of many other therapsids. This dental differentiation is associated with more efficient food processing and higher metabolic rates, and bone histology studies of cynodont specimens indicate rapid growth rates consistent with elevated metabolic activity. High metabolic rates carry energetic costs. They require more food per unit of body mass than lower metabolic strategies, but they also confer advantages in terms of activity levels, thermal regulation, and sustained locomotor performance. In a world where prey required active searching across large areas of impoverished landscape, the capacity for sustained activity may have outweighed the cost of higher food requirements. The prey available to these carnivores was itself limited. Lystrosaurus represented the largest and most abundant prey animal on the landscape, but it was not easily taken. Adult Lystrosaurus, with body masses estimated at tens to potentially over 100 kilograms in larger individuals, would have been beyond the predatory capacity of most early Triassic therocephalians and cynodonts. Juveniles and weakened individuals represented more accessible targets, and the bone beds associated with drought mortality events would have provided periodic carrion opportunities that a flexible omnivore scavenger could exploit. Small procolophonid reptiles, insects, and other arthropods, worms, and whatever aquatic organisms could be accessed from the margins of water bodies, all likely contributed to the diets of these small carnivores. The picture that emerges is one of opportunistic, wide-ranging foragers rather than specialized pursuit hunters targeting specific large prey. Evidence for the behavioral ecology of early Triassic carnivores is necessarily indirect, derived from dental morphology, limb bone proportions, and comparisons with modern animals of similar body plans. Limb proportions in early cynodonts suggest animals capable of relatively sustained locomotion. Neither the explosive burst speed of a specialist ambush predator nor the lumbering gait of a large, slow-moving herbivore, but something intermediate, consistent with active searching behavior across varied terrain. The absence of large prey in the landscape would have favored exactly this kind of locomotor strategy, covering ground efficiently to locate scattered, small, and unpredictable food resources, rather than waiting in ambush for prey that might not arrive. The energetic reality of predation in the early Triassic was stark. In a productive ecosystem, predators can meet their energetic needs within a limited home range, because prey density is sufficient to ensure regular successful hunts. In an impoverished ecosystem, prey density is low, encounter rates are reduced, and the area that a predator must cover to find adequate food increases substantially. For small-bodied predators with high metabolic rates, this creates a compounding problem. The cost of locomotion over large areas must be met by the food obtained from infrequent encounters with small prey. Predators operating under these conditions are, in a real physiological sense, living close to the energetic margin. Population densities of carnivores in such a system would be expected to be very low, and the fossil record is consistent with this expectation. Carnivore fossils from the earliest Triassic are significantly rarer than those of Lystrosaurus, appearing as occasional isolated elements rather than the concentrated assemblages associated with the dominant herbivore. Archosauromorphs were present on the early Triassic landscape, but remained minor components of the carnivore guild during the earliest part of the period. These early reptiles, ancestral to the lineage that would eventually diversify into archosaurs proper, including the ancestors of crocodilians and dinosaurs, were small and apparently opportunistic. Their eventual ecological rise lay far in the future. In the immediate aftermath of the extinction, they occupied peripheral roles in food webs already dominated by the therapsid survivors. The competitive dynamics among these surviving carnivores are difficult to reconstruct with precision, but the available evidence suggests that interference competition, direct conflict over prey or territory, was less significant than exploitation competition. The indirect competition that results when multiple species draw from the same limited resource pool. When prey is scarce, the primary selective pressure on a carnivore is not the behavior of rival carnivores, but the behavior and availability of prey itself. Carnivores in resource-limited systems tend toward dietary generalism, wide-ranging behavior, and tolerance of other predators at shared resource patches, because the energetic cost of aggressive exclusion behavior exceeds the benefit when resources are insufficient to be worth monopolizing. The predators that persisted through the early Triassic did so not by thriving, but by enduring. Their survival was a function of metabolic flexibility, dietary breadth, and the capacity to maintain viable population sizes on a resource base that would have been insufficient to support anything approaching the predator diversity of the Permian. They were the remnants of a predator community that had once been architecturally complex, reduced now to their most adaptable representatives, moving through a landscape that offered little and demanded much. That they persisted at all is a testament to the resilience embedded in their biology, a resilience that would, over millions of years, provide the foundation from which more complex predator communities would eventually re-emerge. While terrestrial landscapes remained sparse and heat-stressed, the waterways of the early Triassic offered something the open land could not: relative stability. Rivers, lakes, and floodplain wetlands buffered their inhabitants against the most extreme temperature fluctuations of the surrounding environment. Water has a high specific heat capacity. It absorbs and releases thermal energy slowly, moderating temperature swings that on exposed land surfaces could be lethal. In a world where air temperatures across equatorial Pangaea periodically reached physiological limits for vertebrate activity, permanent or semi-permanent water bodies represented thermal refugia, zones where conditions remained within survivable ranges even during peak warming intervals. It was in these aquatic and semi-aquatic environments that some of the most ecologically significant survivors of the extinction found their footing. and where the early Triassic produced its most formidable predators. The dominant large predators of early Triassic freshwater systems were not reptiles. They were temnospondyls, a group of large-bodied amphibians with deep Paleozoic roots, whose lineage extended back more than 100 million years before the extinction. Temnospondyls had been diverse and widespread during the Permian, occupying semi-aquatic predator roles across multiple continents. The extinction reduced their diversity substantially, but the group did not disappear. Several lineages persisted into the early Triassic, and in the ecological vacuum left by the loss of more complex predator communities, they expanded into roles that their surviving competitors were poorly positioned to contest. The most prominent of these early Triassic temnospondyls belonged to groups such as the Trematosaurians and the Capitosaurs, broad-skulled, flattened animals with elongated jaws lined with conical teeth, suited for gripping slippery aquatic prey. Body length estimates for the larger individuals of some early Triassic temnospondyl genera reach 2 to 3 meters, with some later Capitosaur relatives achieving lengths approaching 6 meters, though the largest forms postdate the immediate post-extinction interval. Even at 2 to 3 meters, these animals were the largest active predators in most early Triassic freshwater ecosystems. Their skull architecture, wide, dorsally flattened, with eyes positioned toward the top of the head, is consistent with an ambush predator that rested near the surface or on the bottom of shallow water bodies, orienting upward toward prey moving above or at the waterline. The prey available in these river systems included fish, which had survived the extinction in reduced but functionally significant numbers, as well as smaller tetrapods that came to the water's edge to drink or feed. Evidence from stomach contents and associated fossil assemblages is limited for this interval, but the body plan and dental morphology of early Triassic temnospondyls is consistent with the feeding strategies observed in modern ambush aquatic predators, animals that wait in concealment until prey approaches within strike range, then accelerate rapidly over a short distance to secure it. This strategy minimizes energy expenditure, which is significant in a resource-limited ecosystem where the caloric cost of active pursuit could exceed the return from a successful hunt. The rivers and lakes these animals inhabited were themselves products of a disrupted landscape. Early Triassic fluvial systems, as interpreted from sedimentary architecture, were predominantly braided, characterized by wide, shallow channels that shifted position frequently across broad, sparsely vegetated floodplains. Braided river systems develop when sediment supply is high relative to the capacity of vegetation to stabilize riverbanks. In the aftermath of the extinction, with plant cover drastically reduced and root systems unable to bind soil effectively, erosion rates on hill slopes and valley sides increased substantially. This elevated sediment load entered river systems and produced the unstable, laterally mobile channel geometries that appear throughout early Triassic continental sedimentary sequences worldwide. For aquatic predators, braided river systems present specific challenges and opportunities. Channels shift on timescales of years to decades, meaning that habitats can be abandoned or modified rapidly. Isolated pools form as channels migrate, concentrating fish and other aquatic organisms in confined spaces where predation efficiency increases. Seasonal drying would have further concentrated prey into shrinking water bodies during dry periods, creating intervals of locally intense predation opportunity followed by periods of scarcity as water availability declined. Temnospondyl bone beds, accumulations of multiple individuals at single localities, appear at some early Triassic sites and may reflect the aggregation of these animals around persistent water sources during dry seasons, in a pattern broadly analogous to that observed for Lystrosaurus on the terrestrial landscape. Fish communities of the early Triassic were also recovering from extinction-related losses, but they recovered more rapidly than many terrestrial groups. Aquatic ecosystems, while severely affected by ocean anoxia and freshwater chemistry disruption at the extinction boundary, retained more of their basic ecological structure than terrestrial systems. Ray-finned fishes, actinopterygians, diversified relatively quickly in the early Triassic, and their remains are among the more common fossil elements in freshwater deposits of this age. These fish provided the primary prey base for aquatic predators and likely supported a food web of somewhat greater complexity than what persisted on land during the same interval. Alongside the temnospondyls, early archosauromorphs began to appear at the margins of early Triassic water bodies. These were small to medium-sized reptiles, generally under 1 meter in body length, and their ecological role in the earliest Triassic appears to have been minor compared to the temnospondyls. However, their presence in semi-aquatic settings is ecologically significant in retrospect. The archosauromorph lineage would eventually give rise to the crocodilian stem group, animals that would, tens of millions of years later, come to dominate freshwater predator roles globally. In the early Triassic, that eventual dominance was not yet apparent. Temnospondyls held the primary large predator position in freshwater systems, and archosauromorphs occupied subordinate or peripheral roles within those communities. The persistence and relative productivity of early Triassic waterways stands in contrast to the impoverishment of the surrounding terrestrial landscape. Rivers and lakes were not isolated from the broader environmental crisis. Water chemistry disruptions, elevated temperatures, and the collapse of riparian vegetation all affected aquatic systems, but they offered a degree of physical and thermal buffering that the open land surface could not provide. Life concentrated along these corridors. Temnospondyls waited in the shallows. Fish moved through the braided channels. Lystrosaurus and other terrestrial vertebrates returned repeatedly to water sources that were themselves shrinking and shifting across an unstable, sediment-choked floodplain. These waterways were not productive ecosystems in any full sense. They were refugia, narrow corridors of relative viability, threading through a landscape that remained largely inhospitable. The predators that occupied them were not the apex of a complex ecological pyramid, but the largest surviving components of a radically simplified food web. Their size and their ecological persistence in this interval reflect not the richness of the world they inhabited, but the degree to which the extinction had cleared away the competitors and the more complex ecological structures that would otherwise have constrained them. In the empty rivers of the early Triassic, the monsters that remained were those for whom almost everything else had already disappeared. Before the extinction, Earth's terrestrial ecosystems were structured by forests. Not uniformly, the late Permian landscape included arid regions, floodplains, and coastal lowlands with their own characteristic vegetation. But across the mid- and high-latitude zones of Pangaea, and in many equatorial and subtropical regions as well, forests formed the foundational architectural layer of the terrestrial world. They regulated water cycling, stabilized soils, moderated local temperatures, produced the organic matter that fed decomposer communities, and provided the structural habitat within which the majority of terrestrial animal diversity existed. The loss of those forests was not incidental to the end Permian extinction. It was one of its most consequential biological outcomes, and its effects propagated through terrestrial ecosystems for millions of years after the extinction boundary itself. The evidence for forest collapse is preserved in the palynological record, the study of fossil pollen and spores extracted from sedimentary sequences spanning the Permian-Triassic boundary. In the late Permian, pollen assemblages from mid- and high-latitude Gondwana are dominated by the pollen of glossopterid seed plants, a diverse and abundant group of trees and shrubs that formed extensive forested ecosystems across the southern supercontinent. Glossopterid forests were structurally complex, supporting multi-layered canopies, understory vegetation, and the rich decomposer communities associated with sustained organic matter production. Above the extinction boundary, glossopterid pollen disappears from the record. The entire group vanished. In its place, pollen and spore assemblages from the earliest Triassic are dominated by lycopsid spores, the reproductive signature of small, opportunistic spore-producing plants capable of colonizing disturbed and nutrient-poor substrates rapidly. This transition from diverse seed plant pollen to lycopsid spore dominance is documented at Permian-Triassic boundary sections on multiple continents and is one of the most consistent signals of ecological disruption in the terrestrial record. Lycopsids are pioneer species. In modern ecosystems, they appear rapidly after disturbances such as volcanic eruptions, landslides, or severe fires, colonizing bare substrate where more demanding vegetation cannot yet establish. Their dominance in the earliest Triassic palynological record is interpreted as evidence that the terrestrial plant community had been reduced to its most rudimentary successional stage, a landscape in which the complex, slow-growing, resource-demanding seed plants that had structured Permian forests were absent, replaced by fast-colonizing generalists capable of surviving on degraded soils with minimal resources. The absence of coal deposition during the earliest Triassic, the coal gap that extends for several million years above the extinction boundary, reinforces this interpretation. Coal forms through the accumulation, burial, and compression of organic plant matter in waterlogged anoxic environments over extended periods. Its formation requires sustained, high-productivity vegetation growing in stable wetland settings. The global disappearance of coal from the geological record for several million years after the extinction boundary is direct physical evidence that the dense, stable, high-biomass plant communities required for coal formation had ceased to exist on a global scale. The world had lost not just forest cover, but the ecological conditions under which forest cover could persist and accumulate. What replaced the forests on the floodplains and river margins of the early Triassic was sparse, structurally simple, and taxonomically impoverished. Fossil plant assemblages from continental deposits of this age include early conifers, ferns, and horsetails, plants capable of surviving in disturbed, nutrient-poor, and hydrologically variable environments. These were not forests in any meaningful architectural sense. They lacked the height, canopy closure, understory complexity, and biomass density of the ecosystems they had replaced. Their root systems were shallower and less extensive than those of the seed plant forests they followed, meaning their capacity to stabilize soils, regulate water infiltration, and moderate local microclimate was substantially reduced. Soil systems reflected this impoverishment directly. Paleosols, ancient soil profiles preserved in the sedimentary record from the early Triassic, show characteristics consistent with low organic matter input, high disturbance rates, and unstable surface conditions. Calcic horizons, formed by the precipitation of calcium carbonate in soils experiencing net water loss through evaporation, appear at many early Triassic continental localities, indicating arid to semi-arid conditions with insufficient moisture to leach soluble minerals downward through the profile. Vertic features, the deep shrinkage cracks that form in clay-rich soils subject to repeated wetting and drying cycles, are common, reflecting the highly seasonal and episodic nature of moisture availability. The biological component of these soils, the microbial communities, fungal networks, and invertebrate fauna that process organic matter and cycle nutrients in healthy terrestrial ecosystems, is not directly preserved, but the physical characteristics of early Triassic paleosols are consistent with communities impoverished in both diversity and functional capacity. The consequences of forest loss extended beyond the immediate reduction in plant biomass. Forests interact with the hydrological cycle in ways that affect precipitation, river discharge, and regional climate. Through transpiration, the release of water vapor from leaf surfaces, forests return substantial quantities of moisture to the atmosphere, contributing to local and regional precipitation. This feedback, sometimes described as the biotic pump, means that large forested areas effectively generate a portion of their own rainfall. When forests are removed from a region, transpiration declines, atmospheric moisture decreases, and precipitation can decrease in turn. A feedback that reinforces aridity and makes forest re-establishment more difficult. The collapse of Permian forests may therefore have contributed to the aridification observed in early Triassic continental records, not only through the direct effects of climate forcing, but through the disruption of vegetation-climate feedbacks that had previously maintained more humid conditions. Decomposer communities, the fungi, bacteria, and invertebrates responsible for breaking down dead organic matter and returning nutrients to the soil, were also affected by forest collapse, though their record in deep time is fragmentary. In a forest ecosystem, the continuous production and decomposition of leaf litter, woody debris, and root material drives rapid nutrient cycling, keeping nutrients available in the soil for plant uptake. Without this input, nutrient cycling slows, soils become progressively depleted, and the resource base available to recovering vegetation diminishes. Evidence from some Permian-Triassic boundary sections includes what has been described as a fungal spike, an anomalous abundance of fungal spores immediately above the extinction boundary, interpreted as the signature of massive decomposition of dead plant material as forests died synchronously across large areas. If accurate, this represents a brief pulse of intense decomposer activity, followed by the long-term impoverishment of decomposer communities as the input of fresh organic matter collapsed. Animal communities that depended on forest structure were correspondingly affected. The canopy-dwelling niches, the bark and wood-feeding niches, the deep litter insectivore niches, all of these ecological roles had lost their physical substrate. Insects, which had diversified substantially during the Permian in close association with forest ecosystems, experienced significant losses at the extinction boundary, and early Triassic insect assemblages are both less diverse and less abundant than those of the late Permian. The loss of insect diversity had downstream consequences for the small insectivorous vertebrates that depended on them, compressing the lower trophic levels of the terrestrial food web still further. Recovery of forest ecosystems was not a rapid process. The palynological and sedimentological records indicate that it took several million years, through much of the early Triassic, before plant communities in even the most favorable regions began to show the early signatures of increasing structural complexity. The return of seed plant pollen in significant quantities, the re-establishment of stable floodplain soil profiles, and the reappearance of coal-forming environments all occurred gradually and not uniformly across the globe. Some regions recovered earlier than others, reflecting local variations in temperature, moisture availability, and the proximity of plant refugia from which recolonization could proceed. For millions of years, the terrestrial landscapes of Pangaea remained largely open, unstable, and biologically simplified. The horizon was not a wall of canopy, but an expanse of low, scattered vegetation across eroding, sediment-choked floodplains. The forests that had taken hundreds of millions of years to evolve and diversify were gone, and what stood in their place offered only the barest structural foundation for the ecosystems that would eventually need to rebuild within it. The terrestrial devastation of the end Permian extinction was severe and prolonged, but it was in the oceans that the extinction reached its greatest magnitude. Marine ecosystems, which had been building in complexity since the Cambrian explosion more than 500 million years ago, were dismantled with a thoroughness that has no parallel in the subsequent history of animal life. The fossil record of marine invertebrates across the Permian-Triassic boundary documents losses that current estimates place at 90 to 96% of all species, a figure that, when translated into the actual diversity of Permian marine life, represents the disappearance of entire functional groups, body plans, and ecological architectures that had persisted for hundreds of millions of years. The Permian Ocean had been a structured and productive system. Reef ecosystems built primarily by rugose and tabulate corals, calcareous sponges, and bryozoans provided three-dimensional habitat for hundreds of associated species. Brachiopods, filter-feeding organisms with two-valved shells, dominated the seafloor in both diversity and abundance across many environments. Crinoids, relatives of modern sea stars, formed dense communities on hard substrates, extending feathered feeding arms into the water column to capture organic particles. Ammonoids, coiled cephalopod mollusks, moved through the water column in diverse forms, occupying predator and prey roles throughout the marine food web. Trilobites, though already reduced from their Paleozoic peak, still contributed to seafloor communities. This was not a simple system. It was an ecological network of considerable depth, with multiple layers of producers, consumers, and decomposers interacting through relationships refined over geological timescales. Above the extinction boundary, that network was gone. The rugose and tabulate corals disappeared entirely. Both groups went extinct at the boundary and never returned. The brachiopod fauna was reduced to a small fraction of its former diversity, with the few surviving lineages persisting in reduced numbers in restricted environments. Crinoid communities collapsed. Trilobites, already in decline, vanished completely. The ammonoids survived, but barely. The group passed through a severe bottleneck at the extinction boundary, with diversity reduced to perhaps a handful of surviving lineages, from which subsequent Triassic diversification would eventually proceed. What remained in the immediate aftermath was a marine fauna stripped of most of its complexity, dominated by organisms tolerant of disturbed and geochemically hostile conditions. The physical and chemical state of the early Triassic Ocean explains both the severity of the extinction and the difficulty of subsequent recovery. Ocean warming was substantial. Sea surface temperatures in tropical regions reached values estimated at 35 to 40 degrees Celsius, as recorded by oxygen isotope and clumped isotope proxies from carbonate fossils of this age. These temperatures exceeded the thermal tolerances of most reef-building organisms and placed severe physiological stress on the majority of marine invertebrate groups. Thermal stress alone would have been sufficient to drive significant extinction, but it operated alongside a suite of additional stressors that compounded its effects. Ocean acidification accompanied the warming. The same elevated atmospheric carbon dioxide concentrations, responsible for greenhouse heating, dissolved into surface seawater and reacted with carbonate ions to reduce oceanic pH. This acidification lowered the saturation state of calcium carbonate minerals, aragonite and calcite, in seawater, making it progressively more difficult and energetically costly for organisms to precipitate and maintain calcium carbonate shells and skeletons. For reef-building corals, calcareous sponges, brachiopods, mollusks, and echinoderms, groups whose body plans depend fundamentally on the ability to construct carbonate hard parts, acidified ocean conditions represented a direct physiological challenge superimposed on the thermal stress they were already experiencing. Evidence for acidification in the marine record includes the dissolution of carbonate sediments immediately above the extinction boundary at some localities, and geochemical proxies indicating reduced carbonate saturation in early Triassic seawater relative to Permian baselines. Anoxia was perhaps the most spatially extensive of the marine stressors. Warm water holds less dissolved oxygen than cold water, a physical relationship described by the inverse solubility of gases. And as global ocean temperatures rose, the oxygen content of seawater declined. Simultaneously, the thermal stratification of the water column intensified. Warm, less dense surface water floated above colder, denser deep water, reducing the vertical mixing that normally carries oxygen from the surface into the ocean interior. The deep ocean, cut off from atmospheric oxygen resupply and consuming what oxygen remained through the microbial decomposition of sinking organic matter, became progressively anoxic. Evidence for widespread marine anoxia in the early Triassic comes from multiple independent sources. The black, organic-rich shales that form under oxygen-depleted bottom conditions appear throughout early Triassic marine sections globally. Geochemical proxies, including iron speciation data and molybdenum enrichment patterns, indicate anoxic and euthynic conditions, and biomarkers diagnostic of anaerobic photosynthetic bacteria, organisms that require both light and sulfide, conditions that occur only when euthynic water reaches the photic zone, appear at multiple boundary sections, indicating that toxic, sulfide-rich water extended upward into the sunlit surface ocean at certain times and locations. The seafloor communities of the early Triassic reflect these conditions directly. In diverse, well-oxygenated Permian seafloor environments, the sediment surface and shallow subsurface were intensively bioturbated, churned and reworked by burrowing worms, bivalves, crustaceans, echinoderms, and other invertebrates. This bioturbation mixed organic matter into the sediment, oxygenated the shallow sediment column, and created heterogeneous microhabitats that supported diverse communities of associated organisms. In early Triassic marine sediments, bioturbation is dramatically reduced or absent across many sections. Laminated sediments, fine, undisturbed layers that preserve only under conditions where burrowing organisms are absent, are common in early Triassic marine sequences worldwide. Their presence indicates that the seafloor was uninhabitable, or nearly so, for the burrowing invertebrate communities that had previously structured benthic environments. The few organisms that did persist in early Triassic marine settings were those capable of tolerating the combined stresses of elevated temperature, reduced oxygen, elevated carbon dioxide, and fluctuating carbonate chemistry. Microbial mats, communities of bacteria and archaea that had dominated seafloor environments in the Precambrian before the rise of complex animal life, reappeared extensively in early Triassic marine deposits. Microbialites, the carbonate structures produced by these communities, are found at numerous early Triassic marine localities across multiple paleogeographic regions, in environments where they had been rare or absent during the Permian. Their return was not an evolutionary novelty, but a reversion, a filling of ecological space, vacated by the complex invertebrate communities that had previously excluded them through competition and grazing. The reappearance of microbialites in the early Triassic Ocean is one of the clearest indicators of how thoroughly the extinction had rolled back the ecological complexity of marine systems. Some animal groups did persist, and their survival patterns reveal the selectivity embedded within the broader catastrophe. Bivalve mollusks, clams and their relatives survived in greater proportion than brachiopods, despite occupying broadly similar ecological roles as seafloor filter feeders. The reasons for this differential survival are not fully resolved, but current hypotheses point toward differences in respiratory physiology and the mineralogy of their carbonate shells. Bivalves generally have greater physiological tolerance for low oxygen conditions than brachiopods, and their shells are constructed from a mix of carbonate minerals that may have conferred somewhat greater resistance to dissolution under acidified conditions. Fish survived, though with reduced diversity. Some gastropod lineages persisted. Early Triassic marine faunas also included surviving foraminifera, single-celled organisms with carbonate tests, though their diversity was greatly reduced and recovery was protracted. For millions of years following the extinction, the marine realm remained impoverished. Reef ecosystems did not re-establish for approximately 5 million years after the boundary, a gap known as the reef eclipse, because the environmental conditions of the early Triassic were incompatible with the sustained carbonate precipitation and biological complexity that reef construction requires. The open ocean was warm, poorly oxygenated in its deeper layers, and episodically stressed by further geochemical perturbations whose signatures appear as carbon isotope excursions in the marine sedimentary record. Recovery, where it occurred, was localized, tentative, and repeatedly interrupted. The silence of the early Triassic Ocean was not metaphorical, it was structural. The biological machinery that had driven the sounds and movements and ecological interactions of the Permian Sea, the filter feeders drawing water through their tissues, the predators pursuing prey through complex reef architecture, the bioturbators churning the sediment surface, had largely ceased to function. What remained was a diminished system, operating at reduced capacity in a chemically hostile environment, waiting for conditions to shift far enough toward habitability that the slow process of ecological reconstruction could meaningfully begin. Recovery from mass extinction is not a single event, it is a process. And in the case of the end Permian extinction, that process was repeatedly interrupted. The early Triassic Ocean did not stabilize after the initial crisis and then steadily improve. Instead, the geochemical record preserved in marine sediments from this interval documents a succession of perturbations, carbon isotope excursions, renewed anoxic episodes, and pulses of environmental stress that extended across several million years and prevented the sustained ecological rebuilding that recovery requires. The ocean of the early Triassic was not a system in gradual recovery. It was a system in chronic instability, subjected to recurring disruptions that reset or suppressed biological progress each time conditions began to marginally improve. The carbon isotope record is the primary tool through which these perturbations are detected. Carbon exists in two stable isotopic forms, the lighter carbon-12 and the heavier carbon-13. In a biologically productive ocean, photosynthetic organisms preferentially incorporate carbon-12 into their tissues, leaving the surrounding seawater enriched in carbon-13. The ratio of these isotopes, measured from carbonate sediments and organic matter preserved in marine sequences, reflects the balance between biological productivity and the input of isotopically light carbon from sources such as volcanic outgassing, the oxidation of organic matter, or the destabilization of methane-bearing sediments. Disruptions to this balance appear as negative carbon isotope excursions, rapid shifts toward lighter carbon values in the sedimentary record. Multiple such excursions have been identified in early Triassic marine sequences from locations spanning the Paleotethys, the Boreal Sea, and the margins of Panthalassa. These excursions are not uniformly distributed through the early Triassic, but cluster in the earliest part of the period, the Induan and Olenekian stages, before gradually becoming less frequent and less severe as the Triassic progressed. Each excursion represents a geochemical event of sufficient magnitude to leave a measurable signal across geographically distant sections, implying that the responsible perturbations operated at a global or near-global scale. The precise causes of individual excursions remain subjects of ongoing research, but the leading hypotheses involve continued or episodic volcanic activity from the Siberian Trap System, methane release from destabilized seafloor clathrates, and the oxidation of large quantities of organic carbon accumulated in anoxic basins. What these excursions meant for marine life was a series of recurring environmental shocks superimposed on already hostile baseline conditions. Each pulse of isotopically light carbon into the ocean atmosphere system represents an injection of greenhouse gases that would have driven additional warming, further acidification of surface waters, and potentially expanded anoxic zones in the ocean interior. Marine organisms attempting to re-establish populations in the aftermath of the initial extinction were exposed to an ocean that periodically lurched back toward the chemical conditions associated with peak extinction stress. The ecological consequences were not equivalent to those of the extinction boundary itself. The surviving fauna, already filtered through the initial crisis, was composed of the most tolerant lineages. But each perturbation suppressed recovery and imposed additional mortality on populations that were already small, geographically restricted, and physiologically stressed. Anoxic events of the early Triassic were not confined to the deep ocean. Evidence from multiple marine sections indicates that oxygen-depleted water masses periodically expanded upward and laterally, encroaching on shelf environments that would normally have been oxygenated and habitable. Shallow marine shelves, the biologically productive, sunlit zones where most marine invertebrate diversity is concentrated, are vulnerable to anoxia when deep anoxic water masses rise along continental margins in a process called upwelling, or when regional circulation patterns fail to maintain the oxygen supply to bottom waters. In the early Triassic, the combination of a poorly ventilated ocean interior, elevated temperatures, and the periodic injection of additional organic matter from dying biological communities created conditions favorable to the repeated expansion of anoxic conditions into shallow settings. The fossil record reflects these recurring collapses with distinctive stratigraphic patterns. In several early Triassic marine sections, thin intervals of relatively diverse and abundant fossils, indicating brief windows of ecological improvement, are separated by barren or near-barren horizons, dominated by microbial carbonates, black shales, or other indicators of stressed conditions. These alternating layers, sometimes described as boom and bust cycles, represent the repeated establishment and collapse of recovering marine communities. A population of bivalves or gastropods or fish might expand during a favorable interval, only to be reduced or eliminated when the next anoxic episode or thermal pulse reached its habitat. The recovery signal, when viewed across the full early Triassic interval, is therefore not a smooth trajectory of increasing diversity, but a highly irregular pattern of local advances repeatedly interrupted by setbacks. Pyrite, iron sulfide, is a geochemical indicator of particular significance in this context. Pyrite forms in sediments when sulfate-reducing bacteria consume organic matter in the absence of oxygen, producing hydrogen sulfide that then reacts with iron to precipitate iron sulfide minerals. The abundance and isotopic composition of pyrite in early Triassic marine sediments provides independent evidence for the extent and intensity of seafloor anoxia and euxenia. High pyrite abundances in organic-rich early Triassic shales, combined with sulfur isotope values consistent with extensive bacterial sulfate reduction, indicate that the conditions producing toxic hydrogen sulfide in the sediment and overlying water were pervasive and sustained across broad areas of the early Triassic seafloor. The expansion of euxinic conditions, those characterized by free hydrogen sulfide in the water column rather than merely in the sediment, has implications beyond the direct toxicity of sulfide to aerobic organisms. Euxinic water masses, when they impinge on the photic zone, support communities of green and purple sulfur bacteria that conduct anoxygenic photosynthesis, using sulfide rather than water as an electron donor and producing no oxygen as a byproduct. The biomarkers of these bacteria, isoreniaratane, and related compounds derived from the pigments of green sulfur bacteria appear repeatedly in early Triassic marine sediments, confirming that photic zone euxenia was not an isolated or brief phenomenon, but a recurrent feature of the early Triassic ocean in multiple basins. An ocean in which toxic, oxygen-free, sulfide-bearing water reached the sunlit surface layer was an ocean fundamentally hostile to the photosynthetic algae and cyanobacteria that underpin marine food webs. The base of the marine food web, primary production by photosynthetic plankton, was itself disrupted. Geochemical proxies and the record of calcareous nanoplankton, though the latter is less well preserved in the Triassic than in younger sequences, suggest that phytoplankton communities of the early Triassic were both less diverse and less productive than those of the late Permian. Elevated temperatures, acidified surface waters, and the periodic intrusion of euxinic conditions all imposed stress on primary producers. Reduced primary production meant reduced organic carbon flux to the seafloor, less food available for benthic communities, and less organic matter available for the deep-sea microbial communities that ultimately recycle nutrients back into the water column. The entire trophic structure of the ocean was compressed, with reduced energy flowing through every level of the food web. Fish, one of the more resilient groups through the marine extinction, show their own record of post-extinction instability. Early Triassic fish assemblages are generally low in diversity relative to both Permian predecessors and later Triassic successors, but fish were present and feeding throughout the interval. Their presence indicates that the food web, however simplified, retained functional connectivity. There were prey organisms small enough and abundant enough to support fish populations, and the fish themselves supported whatever larger predators remained. But the composition of early Triassic fish faunas changed repeatedly across the interval, with some groups declining and others briefly expanding in patterns that mirror the boom and bust dynamics observed in invertebrate communities. The duration of this instability is significant. The most severe phase of recurring marine perturbations, the interval characterized by the most frequent carbon isotope excursions, the most extensive anoxic episodes, and the most suppressed faunal diversity, spans roughly the first 3 to 4 million years of the Triassic. This is not a brief crisis. It is a sustained environmental regime that maintained the marine realm in a state of chronic ecological depression for a geologically substantial interval of time. The mechanisms that eventually brought this instability to an end were gradual. The waning of Siberian Traps volcanism reduced the input of fresh greenhouse gases. Silicate weathering and carbonate burial slowly drew down atmospheric carbon dioxide. Ocean circulation gradually improved as temperature gradients were re-established. But these processes operated on timescales of millions of years, and the biological communities of the early Triassic Ocean had no mechanism for accelerating them. They could only persist through each successive disruption and expand cautiously during each interval of relative stability, building toward a recovery whose pace was set entirely by the slow chemistry of the Earth system, rather than by the adaptive capacity of the organisms themselves. Ecosystems do not recover uniformly. The process of biological rebuilding after a mass extinction is not a coordinated restoration in which all trophic levels advance together at a steady pace. It is instead a sequential and often asynchronous process, driven by the availability of ecological opportunity at each level of the food web, and constrained by the pace at which the levels below can support those above. Producers must establish before herbivores can expand. Herbivore populations must reach sufficient density before predators can sustain themselves, and predators, requiring larger home ranges, longer developmental times, and greater energetic investment per individual than the organisms they consume, are typically among the last components of a recovering ecosystem to regain ecological significance. In the early Triassic, the gradual return of predator diversity and predator ecological impact was therefore one of the later and more consequential signals of biological recovery, a sign that the food web beneath had developed enough structural depth to support something more complex at its apex. The earliest Triassic predator fauna, as established in preceding context, was sparse and composed primarily of small therapsid carnivores, therocephalians and cynodonts, operating in a landscape nearly devoid of large prey. For the first 1 to 2 million years of the Triassic, this configuration persisted with little fundamental change. But as the period progressed, the ecological landscape began to shift in ways that created new opportunities for predators capable of exploiting them. Herbivore diversity increased modestly. New prey lineages appeared or expanded. Plant communities, though still simplified, produced enough biomass in favorable environments to support denser herbivore populations than the earliest Triassic had sustained. These changes did not occur simultaneously across all regions of Pangaea, and they did not represent a clean transition from one ecological state to another. The process was gradual, geographically variable, and punctuated by the same environmental instability that characterized the broader early Triassic interval. But across this interval, a directional trend is visible in the fossil record. Predator lineages were diversifying, and new predator body plans were beginning to appear. Among the most ecologically significant of these emerging predator lineages were the archosauromorphs, the broader group containing the evolutionary ancestors of archosaurs proper. Early archosauromorphs had been present since the earliest Triassic, but in the initial post-extinction interval, they were small, rare, and ecologically marginal. As the early Triassic progressed, several archosauromorph lineages increased in body size and began to occupy predator roles that had been vacant since the loss of the Gorgonopsians. The transition was not abrupt. It involved a gradual increase in the maximum body sizes achieved by archosauromorph lineages, an expansion in the anatomical diversity of the group, and a corresponding increase in their representation within fossil assemblages relative to the therapsid carnivores that had initially dominated the post-extinction predator guild. The erythrosuchids represent one of the clearest examples of this transition. These large-bodied archosauromorphs appear in the fossil record during the Olenekian stage of the early Triassic, roughly 2 to 4 million years after the extinction boundary, and include animals that reached body lengths of up to 4 or 5 meters in the largest known forms. Their skull architecture is dominated by a large, deep, heavily toothed head, consistent with a predator capable of taking substantial prey. Erythrosuchid limb proportions indicate a more erect posture than many of their predecessors, suggesting locomotor efficiency improvements that would have supported more active predatory behavior. The appearance of animals of this body size in the predator guild represents a qualitative shift in the structure of early Triassic terrestrial food webs. For the first time since the extinction, a predator existed that was large enough to routinely prey on adult Lystrosaurus and other medium to large herbivores. The ecological implications of this shift extended beyond the immediate predator-prey relationship. The presence of a large apex predator in a recovering ecosystem introduces top-down regulatory effects that were absent during the earliest Triassic. Prey animals modify their behavior in response to predation pressure, altering foraging patterns, habitat use, and group behavior in ways that affect vegetation recovery, soil disturbance, and the spatial distribution of ecological activity. The reintroduction of meaningful top-down regulation into early Triassic terrestrial ecosystems, even in its early and limited form, would have begun to add structural complexity to communities that had previously been regulated almost entirely from the bottom up by resource availability. Cynodont lineages also continued to diversify during this interval. While the earliest Triassic cynodonts had been small and generalistic, later, early Triassic forms showed increasing anatomical differentiation, a pattern consistent with the beginning of ecological divergence among lineages that had previously occupied similar generalist roles. Some cynodont lineages showed dental specializations consistent with more efficient herbivory or omnivory, while others retained the carnivorous or insectivorous dentitions of their predecessors. This dietary diversification among cynodonts is significant because it represents the beginning of the ecological differentiation that would eventually produce, over tens of millions of years, the extraordinary diversity of the mammalian lineage. In the early Triassic, that outcome was not yet visible in the fossil record, but the first small steps toward it, the divergence of cynodont ecologies into distinct functional roles, were beginning to accumulate. In marine environments, the return of predatory lineages followed a parallel but distinct trajectory. Fish, which had maintained relatively continuous presence through the marine extinction and its aftermath, diversified gradually across the early Triassic, and with increasing fish diversity came increasing ecological complexity within the water column food web. Marine reptiles began to appear in the fossil record during this interval. Ichthyosaurs, highly derived, fully aquatic reptiles with streamlined body forms adapted for fast, sustained swimming, appear in early to middle Triassic deposits, and their emergence represents one of the most rapid and dramatic ecological transitions in the vertebrate fossil record. The earliest ichthyosaurs were already substantially committed to an aquatic lifestyle, with limbs modified into flippers and body proportions suggesting active pursuit predation in the open water. Their appearance in the marine record indicates that at least some lineages of terrestrial or semi-aquatic reptiles had transitioned to marine life with sufficient speed to leave no clear fossil record of the intermediate stages. The prey that supported early marine predators was itself recovering. Ammonoid cephalopods, whose diversity had been reduced to a handful of surviving lineages at the extinction boundary, underwent a series of rapid diversification events during the early Triassic, repeatedly expanding their morphological and ecological range before being reduced again by environmental perturbations. This pattern of rapid diversification, followed by extinction and rediversification, sometimes described as a diversification relay, is one of the most distinctive features of early Triassic ammonoid evolution. It reflects the instability of the marine environment during this interval. Conditions periodically improved enough to allow explosive expansion of opportunistic lineages, but then deteriorated sufficiently to collapse those same lineages, opening ecological space for the next wave of diversification. The net result, across the full early Triassic, was a gradual accumulation of ammonoid diversity punctuated by repeated resets, a trajectory that would eventually contribute to the rich ammonoid faunas of the later Triassic and Jurassic. Benthic marine communities showed comparable, if slower, signs of increasing complexity. Trace fossil assemblages, the preserved burrows, trails, and feeding traces left by organisms moving through seafloor sediment, provide a particularly sensitive record of benthic community recovery, because they capture not just the presence of organisms, but their activity and behavioral diversity. In the earliest Triassic, trace fossil assemblages are dominated by simple, shallow, horizontal traces consistent with organisms conducting minimal bioturbation under low oxygen, stressed conditions. As the early Triassic progressed and anoxic episodes became less frequent, trace fossil assemblages show a gradual increase in ichthyodiversity, the variety of trace types, and in the depth of bioturbation, reflecting the return of more diverse and more active benthic communities capable of reworking sediment more thoroughly. This signal, subtle in any individual section, is consistent across multiple geographically distinct marine localities and represents one of the most reliable records of genuine ecological recovery in the early Triassic marine realm. The return of predators to meaningful ecological roles, both on land and in the ocean, was not simply an addition to the recovering ecosystem. It was a signal that the system had developed enough structural depth to sustain them. Predators require prey. Prey requires producers. The reappearance of predators capable of taking large prey, navigating open water, or sustaining populations across broad geographic ranges indicated that the trophic layers beneath them had recovered sufficiently to provide that support, at least intermittently and in at least some regions. The food web was not yet rebuilt. The diversity of the Permian had not been restored, but the architecture of a more complex biological system was beginning, slowly and unevenly, to reassemble itself from the components that the extinction had left behind. Recovery from the end Permian extinction was not a single turning point. It did not arrive at a moment that can be identified in a single sedimentary layer or marked by the appearance of a single taxon. It was instead an accumulation, a slow, geographically uneven, repeatedly interrupted process of ecological rebuilding that expressed itself differently across different environments and at different latitudes. But across the full span of the early Triassic and into its transition toward the middle Triassic, the directional signal is present in the fossil and geochemical record. The planet was, gradually and incompletely, beginning to recover the biological complexity it had lost. The clearest early signals of recovery come from the physical environment rather than from the biological record directly. Atmospheric carbon dioxide concentrations, though they remained elevated throughout the early Triassic, show a long-term declining trend through this interval, as the rate of volcanic input from the Siberian trap system waned, and as silicate weathering reactions, which consume carbon dioxide from the atmosphere, continued to process the fresh volcanic and sedimentary rock exposed by erosion and tectonic activity. The timescale of this drawdown was not years or centuries, but millions of years, operating through the slow geochemical cycling of carbon between the atmosphere, ocean, and lithosphere. As carbon dioxide declined, so too did the intensity of greenhouse warming, and global mean temperatures began a protracted decrease from the peak values of the earliest Triassic toward the somewhat lower, though still elevated, values characteristic of the later Triassic. The moderation of temperature had cascading effects throughout the Earth system. In the oceans, cooler surface temperatures increased the solubility of oxygen in seawater and reduced the intensity of thermal stratification, allowing improved ventilation of intermediate and deep water masses. Anoxic and euthynic conditions, while they did not disappear immediately, became less spatially extensive and less persistent as ocean circulation improved. The frequency of the carbon isotope excursions that had punctuated the earliest Triassic declined, indicating that the geochemical perturbations driving those excursions were becoming less severe or less frequent. The ocean's chemical environment was moving, slowly, toward conditions more compatible with sustained biological productivity and ecological complexity. On land, the response to moderating temperatures and changing precipitation patterns was expressed most clearly in the recovery of plant communities. The lycopsid-dominated pioneer vegetation of the earliest Triassic gave way gradually to assemblages of increasing compositional diversity. Fossil pollen and spore records from early to middle Triassic continental sequences document the progressive return of seed plant pollen, initially in small quantities and in geographically restricted localities, but increasing in abundance and geographic extent across the interval. Conifers, which had survived the extinction as a minor component of the flora, began to diversify and expand their ranges. Early representatives of other seed plant groups appeared. The fern communities that had persisted through the crisis continued to diversify in form and ecology, contributing to increasingly stratified vegetation structures in humid environments. The return of seed plants to ecological significance had consequences that extended well beyond the composition of the flora itself. Seed plants, by virtue of their deeper root systems, greater height, and higher rates of transpiration relative to pioneer ferns and lycopsids, began to restore the vegetation climate feedbacks that had been disrupted by forest collapse. As plant cover increased and became more continuous, soil stabilization improved, reducing erosion rates and allowing the development of more mature soil profiles. Organic matter inputs to soils increased, supporting the gradual recovery of soil microbial communities and the nutrient cycling processes they mediate. River systems, their catchments increasingly stabilized by vegetation, began to transition from the braided, sediment-choked configurations of the earliest Triassic toward more stable, meandering channel forms, a sedimentological signal preserved in the changing architecture of fluvial deposits across the early to middle Triassic transition. Wetland and floodplain environments were among the first to show signs of increased biological complexity because they combined moisture availability with the nutrient inputs delivered by flooding, conditions that favored rapid plant growth and provided habitat for aquatic and semi-aquatic animal communities. Fossil plant assemblages from early Triassic floodplain settings are generally more diverse than those from contemporaneous upland or interior environments, and it is from these waterlogged, nutrient-rich settings that some of the earliest signs of recovering plant community structure are recorded. Horsetails, sphenopsid plants capable of rapid growth in disturbed wet conditions, formed dense stands along river margins, and their hollow stems and jointed architecture provided structural habitat for invertebrate communities in a landscape that was otherwise poorly structured. The recovery of invertebrate communities on land is less well documented than that of vertebrates or plants, because the preservation potential of insects and other arthropods in continental sediments is generally low. But what evidence exists suggests that insect diversity increased through the early Triassic, with new lineages appearing and diversifying as plant communities provided expanding resources in the form of leaves, stems, wood, and the decomposing organic matter that accumulates in stable, vegetated environments. The recovery of insect communities had direct implications for vertebrate recovery because insects represent a critical food resource for small vertebrates, the trophic foundation upon which the diversification of small-bodied tetrapods depends. In marine environments, the signals of recovery accumulated on comparable timescales, but with their own characteristic patterns. The trace fossil record, as previously noted, shows a progressive increase in ichnos and bioturbation depth through the early Triassic, a signal that benthic communities were becoming more diverse and more ecologically active. By the later part of the early Triassic and into the earliest Middle Triassic, some marine sections record the first reappearance of reef-like structures built by organisms other than microbial mats. These early post-extinction reefs were not comparable in complexity or extent to the Permian reefs they followed. They were constructed primarily by sponges and by microbe-sponge associations rather than by corals, and they were small, geographically restricted, and ecologically simple relative to the architectural complexity of Permian reef systems. But their appearance marks a genuine threshold, the first evidence that carbonate-secreting organisms had recovered sufficient population sizes and had encountered sufficiently hospitable chemical conditions to begin constructing three-dimensional reef structures again. The ammonoid record through this interval provides one of the most quantitatively detailed pictures of marine recovery dynamics available for the early Triassic. Ammonoid diversity, which had been reduced to a handful of lineages at the extinction boundary, increased episodically through the early Triassic in the pattern of repeated diversification and collapse described earlier. But the longer-term trend, when viewed across the full interval, was one of net diversity accumulation. Each diversification event, even when followed by a reduction, tended to leave behind a somewhat larger residual diversity than had existed before it, a ratchet-like progression that slowly rebuilt species richness even in the face of repeated setbacks. By the end of the early Triassic, ammonoid diversity had recovered substantially from its post-extinction nadir, and the group was positioned to contribute to the increasingly complex marine ecosystems of the Middle Triassic. Vertebrate communities on land showed their own recovery trajectory. The extreme dominance of Lystrosaurus that characterized the very earliest Triassic had diminished by the later part of the early Triassic. As other lineages expanded, and the relative abundance of Lystrosaurus in fossil assemblages declined, procolophonid reptiles diversified into a range of small-bodied ecological roles. Cynodont diversity increased. Archosauriform lineages expanded in body size and ecological variety. The composition of terrestrial vertebrate assemblages became progressively less monotonous, not yet approaching the ecological complexity of the late Permian, but showing clear evidence of increasing taxonomic and functional diversity relative to the extreme simplicity of the earliest post-extinction communities. The concept of ecological succession is useful for understanding this process. In modern ecosystems, disturbed habitats recover through a sequence of successional stages, beginning with pioneer communities of generalist, fast-growing species and progressing through intermediate stages of increasing complexity toward mature, species-rich communities with high functional redundancy and ecological stability. The early Triassic represents something like a succession operating at the scale of the entire biosphere, a planetary-scale ecological recovery progressing through stages defined by the appearance and expansion of increasingly complex biological communities. The process was slower, more variable, and more frequently interrupted than succession in a modern disturbed habitat, because the disturbance had been more severe and the environmental conditions during recovery remained hostile for far longer. But the underlying dynamic was comparable: pioneer taxa giving way to more diverse assemblages, simplified food webs acquiring additional trophic levels, and physical environments being progressively modified by the organisms inhabiting them in ways that facilitated further biological expansion. By the close of the early Triassic, approximately 247 million years ago, the planet was measurably different from the world that had existed in the immediate aftermath of the extinction. It was not yet a fully recovered world. The diversity of the late Permian had not been restored. The ecological complexity of its marine and terrestrial systems remained well below Permian levels. Environmental instability had not entirely ceased, but the trajectory had changed. The indicators of acute crisis, the most severe carbon isotope excursions, the most extensive anoxic episodes, the most extreme thermal anomalies, were becoming less frequent and less intense. The biological signals of recovery, increasing diversity, expanding body size ranges, the reappearance of ecologically complex structures like reefs and stable floodplain forests, were accumulating across multiple independent records. The Earth system, having absorbed the most severe biological catastrophe of the Phanerozoic, was slowly reasserting its capacity to support complex life. The therapsids had dominated the Permian terrestrial world. They had produced the largest herbivores, the most formidable carnivores, and the most ecologically diverse vertebrate fauna of the late Paleozoic. Through the extinction and into the earliest Triassic, they retained a degree of this dominance. Lystrosaurus as the overwhelmingly abundant herbivore, Therocephalians and cynodonts as the primary small carnivores, but this persistence was increasingly the residue of a former era rather than the foundation of a new one. As the early Triassic progressed, a different group of vertebrates began to assert themselves across the recovering landscape, not through a single dramatic displacement of the therapsids, but through a gradual process of ecological expansion that would, over the course of millions of years, fundamentally restructure terrestrial vertebrate communities. That group was the archosaurs and their close relatives, the reptilian lineage whose eventual dominance would define the Mesozoic world. The term archosaur, in its strict phylogenetic sense, refers to the crown group containing the last common ancestor of modern crocodilians and birds and all of its descendants. In common paleontological usage, it also encompasses the broader Archosauriform clade, the larger group that includes archosaurs proper along with their extinct stem relatives. It is within this broader group that the first significant expansions of reptilian ecological dominance occurred during the Triassic. The Archosauriforms as a whole are distinguished by a suite of anatomical features that collectively enhanced locomotor efficiency, predatory capability, and metabolic performance relative to many earlier reptile groups. These include the antorbital fenestra, an opening in the skull between the eye socket and the nostril, whose function is debated, but which is associated with structural modifications of the skull that may have improved bite mechanics, along with modifications to the ankle joint that allowed more efficient terrestrial locomotion, and teeth set in deep sockets that were replaced throughout life. providing a continuously renewed dentition suited for active predation. The erythrosoucids, which had appeared during the Olenekian stage of the early Triassic as the first large-bodied archosauriform predators, represented an early expression of this ecological expansion. Their body sizes, reaching 4 to 5 meters in the largest known forms, placed them well above any therapsid carnivore of the same interval and gave them access to prey that smaller predators could not efficiently exploit. But the erythrosoucids were not archosaurs in the strict sense. They were stem archosauriforms, relatives of the archosaur lineage that arose before the evolutionary divergence that would eventually produce the crocodilian and bird lineages. Their ecological importance lay not in their own long-term evolutionary trajectory, but in the fact that they demonstrated, early in the Triassic, that the archosauriform body plan was capable of scaling to large size and dominating the apex predator role in terrestrial ecosystems. True archosaurs, defined by the presence of a fully developed archosaurian ankle configuration and a suite of associated cranial and postcranial features, appear in the fossil record during the Middle Triassic, slightly beyond the strict 10 million year window of the early Triassic. But the ecological groundwork for archosaur dominance was laid during the early Triassic, through the successive appearance and expansion of progressively more derived archosauriform lineages that occupied predator roles of increasing size and complexity. The proterochampsids, the proterosoucids, and the broader radiation of early archosauriforms collectively represent a stepwise ecological expansion of the archosauriform body plan into niches that the extinction had vacated and that therapsids had failed to fully reoccupy. Proterosoucids, among the earliest and most basal of the archosauriform groups, appear at or very near the Permian-Triassic boundary in deposits from South Africa, Russia, and China. These animals were elongated, with relatively long necks and tails, and were likely semi-aquatic or capable of movement both in water and on land. Their dentition suggests active predation on fish and small tetrapods, and their early appearance in the post-extinction record, essentially contemporaneous with Lystrosaurus in some localities, indicates that the archosauriform lineage was among the earliest reptile groups to establish a presence in the post-extinction world. Their ecological role in the very earliest Triassic was modest, but their presence established a foothold from which subsequent archosauriform diversification would proceed. Tanistrophiids represent a particularly distinctive component of the early archosauromorph radiation. These animals, known from early and middle Triassic deposits, achieved body forms that deviate substantially from the generalized archosauriform template. Some Tanistrophiid genera possessed extraordinarily elongated necks. In the largest forms, the neck constituted more than half of the animal's total body length and was composed of a small number of highly elongated cervical vertebrae. The functional interpretation of this anatomy has been debated, but isotopic analysis of Tanistrophiid teeth from some localities suggests a diet heavily weighted toward aquatic prey, consistent with a neck used to extend the head toward water surfaces or into aquatic environments to capture fish and cephalopods. Tanistrophiids illustrate the degree of morphological experimentation that characterized the archosauromorph radiation during the Triassic, a group exploring a wide range of body plans and ecological strategies in the context of an ecologically open world. The rhynchosaurs, a group of archosauromorphs that developed herbivorous ecologies, also expanded during this interval. Early rhynchosaurs were small and likely fed on tough plant material, but the group diversified considerably across the Triassic and at some localities became among the most abundant medium-sized herbivores of the Middle Triassic landscape. Their ecological expansion reflects the broader opportunity that the recovering terrestrial world presented to lineages capable of processing plant material efficiently, a role that had been almost exclusively occupied by therapsids during the Permian and earliest Triassic. The appearance of archosauromorph herbivores in significant numbers represents the beginning of a long-term shift in the composition of terrestrial herbivore communities, from therapsid-dominated to archosaur-dominated, that would be completed over the course of the Triassic. The therapsids themselves did not disappear during this interval. Dicynodonts, the group to which Lystrosaurus belonged, diversified during the Middle Triassic, producing forms substantially larger than Lystrosaurus itself, with some later Triassic dicynodonts reaching body masses comparable to large modern herbivores. Cynodonts continued to diversify and refine their anatomical organization, moving progressively toward the physiological and anatomical configurations that would eventually characterize mammals. But the overall trajectory of therapsid evolution during the Triassic was one of gradual contraction from ecological dominance rather than expansion. The large herbivore roles, the apex predator roles, and eventually the medium-bodied omnivore roles that therapsids had occupied in the Permian were progressively filled by archosaur and archosauriform lineages as the Triassic proceeded. The therapsids retained a presence, and their cynodont descendants would ultimately produce the mammalian lineage, one of the most successful vertebrate radiations in Earth history. But the age of therapsid ecological supremacy was drawing to a close. What drove this transition was not straightforwardly competitive superiority of archosaurs over therapsids in a direct, one-to-one ecological contest. The picture that emerges from the fossil record is more complex. In the immediate aftermath of the extinction, therapsids held their ecological positions because they had survived and archosaurs were scarce. As archosauriform lineages diversified and increased in body size, they occupied ecological roles, particularly large-bodied apex predation, that therapsids had vacated and not reoccupied. The subsequent expansion of archosaurs into herbivore roles occurred in an ecological landscape that was itself changing. Plant communities were recovering, new vegetation types were expanding, and the character of the terrestrial environment was shifting in ways that may have differentially favored the archosaurian body plan. Archosauriform locomotor anatomy, particularly the more erect limb posture and the efficient ankle joint configuration, may have provided energetic advantages in the context of active foraging across the expanding and increasingly varied landscapes of the recovering Triassic world. A more erect posture reduces the energetic cost of sustained locomotion relative to the sprawling posture of many earlier reptiles. And in a world where food resources were still widely distributed and required active searching to locate, locomotor efficiency was a genuine selective advantage. These anatomical differences did not determine the outcome of therapsid-archosaur ecological competition by themselves, but they may have systematically biased the long-term ecological trajectory of the two groups, in an environment where sustained locomotor performance was at a premium. The first reptile empires of the early middle Triassic were not yet the dinosaur-dominated world that would follow. They were more tentative, more ecologically mixed, and more geographically variable than the later Mesozoic configurations they foreshadowed. But within them, the foundations of that later world were being constructed. In the expanding body sizes of archosauriform predators, in the diversifying ecologies of archosauromorph herbivores, and in the progressive establishment of the ecological architectures that archosaurs would carry forward into the age that was still millions of years away. The world that emerged from the early Triassic was not the world the extinction had destroyed. It was something new, ecologically reorganized, taxonomically restructured, and populated by lineages whose evolutionary trajectories had been fundamentally redirected by the crisis they had survived. The path from the barren floodplains of the earliest Triassic to the dinosaur-dominated ecosystems of the late Triassic and Jurassic was neither direct nor inevitable. It passed through a series of ecological configurations that were each complete in themselves, each representing a distinct stage in the long process of biological reconstruction that the end Permian extinction had set in motion. Understanding that path requires tracing the diversification of the Archosaur lineage across the Middle and Late Triassic, a radiation that would eventually produce the most ecologically dominant vertebrates in the history of terrestrial life. The Archosaurs that diversified across the Middle Triassic inherited a world that was recovering but still restructuring. Plant communities were expanding in diversity and geographic extent, but the global forest had not been restored to its Permian configuration. New vegetation types, dominated by conifers, seed ferns, and cycad relatives, rather than the glossopterid and caudatalian forests of the Permian, were establishing themselves across different regions of Pangaea, creating a mosaic of habitats that differed in structure, productivity, and the ecological opportunities they presented. River systems were stabilizing, soils were deepening, the biological framework within which animal communities operated was becoming richer and more varied, and archosaurs were positioned, by their anatomy and their timing, to exploit that expanding framework more effectively than most of their contemporaries. Early in the Middle Triassic, the Archosaur lineage split into two major evolutionary branches whose subsequent histories would define the Mesozoic world. One branch, the Pseudotsuchians, sometimes called the crocodilian line, diversified into a remarkable range of ecological forms during the Triassic, including bipedal predators, armored herbivores, and large-bodied apex carnivores. The other branch, the ornithoderans, sometimes called the bird line, initially diversified more quietly, producing small-bodied forms before eventually giving rise to the pterosaurs and, ultimately, the dinosaurs. In the Middle Triassic, neither branch had yet achieved the ecological dominance it would later attain. Both were components of mixed communities that still included substantial therapsid diversity, and the outcome of their eventual ecological competition with each other and with surviving therapsid lineages was not yet determined. The Pseudotsuchian radiation of the Middle and Late Triassic produced a diversity of body forms that rivals, in its ecological breadth, the later radiation of the dinosaurs themselves. Atosaurs, heavily armored, quadrupedal herbivores with small heads and leaf-shaped teeth, spread widely across late Triassic Pangaea and were among the most abundant herbivores in some localities. Rauisuchians, large-bodied, fully terrestrial predators with more erect limb postures than earlier Archosaur relatives, occupied apex predator roles across multiple continents during the late Triassic, reaching body lengths of 6 meters or more in the largest forms and filling the ecological roles that would later be occupied by large theropod dinosaurs. Phytosaurs, superficially crocodile-like animals with elongated skulls and semi-aquatic habits, dominated freshwater predator communities across much of the late Triassic, occupying the ecological position that true crocodilians would later assume. This Pseudotsuchian radiation represented, for much of the Triassic, the dominant expression of Archosaur ecological diversification on land and in freshwater systems. Against this Pseudotsuchian diversification, the earliest dinosaurs appear initially modest. The oldest unambiguous dinosaur fossils recovered from Middle to Late Triassic deposits in South America, particularly from the Ischigualasto Formation of Argentina, date to approximately 230 to 233 million years ago. These earliest dinosaurs were small to medium-sized animals, generally bipedal, and occupied predator or omnivore roles in communities where pseudoseuchian archosaurs were often more numerous and more ecologically diverse. Eoraptor, Eodromeus, and Herrerasaurus, among the best-known early dinosaurs, represent the initial expression of the dinosaurian body plan, a relatively lightly built bipedal form with grasping forelimbs, a fully erect hindlimb posture, and a range of dental morphologies reflecting dietary variation within the early dinosaur radiation. The anatomical features that distinguished early dinosaurs from their archosaur relatives were not dramatic in isolation, but their combination produced a body plan with significant functional consequences. Full hind limb erection, in which the femur moves in a parasagittal plane directly beneath the body rather than extending laterally, improves locomotor efficiency and increases stride length relative to semi-erect or sprawling postures. Open acetabulum anatomy, the configuration of the hip socket that accommodates fully erect locomotion, appears in dinosaurs and is one of the defining features of the group. High growth rates, inferred from bone histology in early dinosaur specimens, suggest elevated metabolic rates compared to many contemporary reptiles, with implications for sustained activity levels and thermoregulatory capacity. These features collectively positioned early dinosaurs as active, fast-growing, metabolically dynamic animals in a world where such attributes had demonstrated survival value across millions of years of post-extinction ecological pressure. The ecological context into which early dinosaurs diversified was one in which large predator and large herbivore roles were already occupied by Rauisuchians and Etosaurs respectively among the pseudoseuchians, and by surviving dicynodont therapsids in the herbivore guild. Early dinosaurs were not, in their initial radiation, displacing these incumbents through direct competitive superiority. They were diversifying into the ecological spaces available to them, smaller predator and omnivore roles initially, with gradual expansion into larger body sizes and more diverse ecological positions as the Triassic progressed. The mechanisms by which dinosaurs eventually came to dominate terrestrial ecosystems globally remain a subject of active research and debate. The traditional view of competitive superiority, dinosaurs outcompeting pseudoseuchians through superior locomotion or metabolism, has been complicated by more recent fossil discoveries, indicating that the transition was neither rapid nor straightforwardly competitive. A major factor in the eventual rise of dinosaur dominance was a further extinction event at the end of the Triassic, approximately 201 million years ago, that disproportionately affected pseudoseuchian archosaurs and large-bodied therapsids, while leaving the dinosaur lineage comparatively intact. This end Triassic extinction, driven by volcanism associated with the opening of the Central Atlantic magmatic province as Pangaea began to fragment, removed many of the ecological competitors that had constrained dinosaur diversification throughout the Triassic. In its aftermath, dinosaurs expanded rapidly into the ecological roles vacated by pseudoseuchians and therapsids, initiating the Jurassic radiation that would eventually produce the full diversity of sauropods, theropods, and ornithischians familiar from the later Mesozoic record. The connection between the end Permian extinction and the eventual rise of dinosaurs is therefore not a simple causal chain, but a longer and more contingent historical process. The extinction created the ecological conditions, empty niches, simplified communities, disrupted competitive hierarchies, within which the therapsid survivors initially dominated, and within which archosaur lineages subsequently diversified. The Archosaur radiation of the Triassic produced the Pseudosuchian and Ornithodiraen branches, whose interactions, over tens of millions of years, shaped the ecological landscape into which early dinosaurs appeared. And the end Triassic extinction then cleared the ecological stage in a manner that allowed dinosaurs specifically, among all the Archosaur lineages, to achieve global dominance. Each of these steps was contingent on the one before it, and each involved the action of environmental forces, volcanism, climate change, ocean chemistry, operating independently of the biological trajectories they influenced. The middle and late Triassic landscapes across which these transitions unfolded were themselves the products of the long recovery from the end Permian event. The expanding conifer forests of the late Triassic, the increasingly complex river and lake systems of the recovering continental interior, the diversifying insect communities that supported the small-bodied vertebrate fauna, all of these were the cumulative result of millions of years of ecological rebuilding that had begun in the barren, heat-stressed floodplains of the earliest Triassic. The road to the dinosaurs passed through every stage of that recovery, through the Lystrosaurus-dominated wastelands, through the sparse predator communities of small therapsids, through the expanding archosauriform radiations of the early and middle Triassic, and through the complex, Pseudosuchian-dominated ecosystems of the late Triassic that dinosaurs would ultimately inherit. It was a road built not by design, but by survival, by the accumulated persistence of lineages that had endured conditions no complex vertebrate community had previously faced, and whose descendants, shaped by those conditions, would go on to populate a world defined by the catastrophe their ancestors had survived.